Yo, yo, yo. Welcome to Chemical Reactions, Law of Conservation of Matter. By the end of the day, you should be able to define and explain the law of conservation of mass, represent chemical reactions and the conservation of atoms using molecular models. What is a chemical reaction? Turn to page 9 in your spiral and find some free space on the page, maybe in between the Alka-Seltzer demo and the product slide, or at the very bottom of the page to write our definition. Notice in the animation that we have these two hydrogen molecules seen in green, and this one oxygen molecule seen in red. Now they come in and they collide, and after that collision, atoms are rearranged, and they form these new substances. This, y'all, is a chemical reaction. So let's write down our definition. A chemical reaction is when atoms of one or more substances are rearranged to form new substances. And this is our key word here, y'all. Rearranged to form new substances. What is evidence of a chemical reaction? So if we were to witness this reaction, what is some evidence that we might see or feel or hear? One really obvious piece of evidence would be a temperature change. I'm going to write that down. Temperature change. Another piece of evidence would be bubbles or gas being released, or color change. Now, how do we write this? How do we represent these chemical reactions? Well, chemists use equations to represent reactions. We spent a lot of last semester learning how to write chemical formulas for ionic, covalent, and metallic substances. So we're going to use those chemical formulas to write equations that represent what's happening in the animation. You see here, generally speaking, we have reactants that are converted to products. On page 9 in your spiral, you'll see several boxes. On the top right-hand side, you'll see reactants, and on the bottom left-hand side, you'll see products. You should also see this chemical equation listed here. Now, we're going to use this to help us define what reactants and products are. So let's first start with reactants. On your page, you should see a line here on these two. And we're going to label it reactants. These two chemical formulas, H2 and O2, represent these models down here. What exactly are reactants? Well, at the bottom of that box for reactants, let's go ahead and write down they are found on the left-hand side. So first note, they are found on the left-hand side. When I refer to left-hand side, I am actually saying that is anything to the left of this arrow here. Anything left of it is considered left-hand side of the equation. And the other important feature is that bonds are broken. Okay, the bonds in the reactants must be broken. So bonds must be broken. So as I'm looking at my model here, to convert these reactants to my products, these water molecules, I have to break this bond between the two hydrogen atoms, this bond as well between the two hydrogen atoms, and this bond right here between the two oxygen atoms. When these bonds break, y'all, my products can finally be formed. So at the bottom of that box, you've written down both important pieces of information, that reactants are found on the left-hand side of the arrow and that bonds in reactants must be broken. Now we're going to fill in our definition for products. Let's go ahead and label that this is the product. Here our products are found on the right, and again, we're referring to the right-hand side of the arrow. So again, they are located on the right-hand side. We are also going to write down that our products are the result of new bonds being formed. So new bonds being formed. So when the bonds between the hydrogen atoms and the oxygen atoms are broken, new bonds between hydrogen and oxygen atoms can be formed. And I'm going to highlight those new bonds here and here. So these are the new bonds being formed. So products are found on the right, and they represent new bonds being formed. Chemical reactions can be written as equations to show the reactants and products. We can use a word equation like nitrogen monoxide plus oxygen yields nitrogen dioxide. And I want to take a quick note of this arrow. It means yield, or to produce, or create. Or we can use a symbolic equation. We're going to spend most of our efforts on these symbolic equations that use formulas to represent our reactants and our products. If you look at page 9 on the bottom right-hand corner, you'll see the word coefficient. So coefficient in our example would be these big numbers in front. I know you don't see a number in front of oxygen, and if you don't see a number, it simply means the number 1. In algebra, we don't write down 1x, we only write down x. So again, similarly, we don't write down O2, we just simply write O2. So let's take a look at the official definition. What does coefficient mean? It indicates how many of each molecule there are. So those big numbers in front indicate how many of each molecule there are. I want you guys to write down for the coefficient definition the following here. It is the big numbers in front. Okay, and those big numbers tells us the number of molecules there are. So what does the coefficient exactly tell us? It tells us the required number of molecules for this reaction to occur. So if I take a look at my example, I underlined it, and I see that this reaction requires 2 nitrogen monoxide molecules. So I'm going to draw that out for y'all. So 2 nitrogen monoxide molecules. N is going to be in red, and nitrogen or oxygen is going to be in blue. So right now I have 1 nitrogen monoxide molecule, but that coefficient says I need 2. So I'm simply going to draw another one. Nitrogen, red, oxygen, blue. So here we have it. The 2 is now illustrated. I have 2 molecules of NO. Next, if you guys turn your page over, and on the top right-hand side, you'll see the word state of matter. This means the letters that indicate the state of each compound. I'm confident that you guys are familiar with solid, liquid, and gases. So let's put that down. S is for solid, L for liquid, G for gas. And the most important one, in my opinion, would be AQ. AQ stands for aqueous. Again, aqueous. And aqueous means a substance that has been dissolved in water. Most of the chemical reactions that we observe are aqueous solutions. So something that's been dissolved in water and we're mixing those components together. So that's aqueous substance that's been dissolved in water. On the left-hand side, you'll see subscripts. So subscripts are these small numbers that you guys see here. Okay? They indicate how many atoms there are of each element in a molecule. Again, they're the small numbers at the bottom. So I'm going to write that right next to the subscripts, right here, small numbers at the bottom. They indicate how many atoms there are of each element in a molecule. So if I were to take a look at my example right here, NO2. What does that tell me? Well, the 2 there tells me that there are 2 oxygen molecules. So if I'm using the same color system that I had before, NO2, N was red, and then the oxygen, there is 2 oxygens attached to the red nitrogen. So that's what that means there. I have 2, so 1, 2 oxygens, and I only have 1 nitrogen. If you don't see a subscript again, it simply means 1, but we don't write that for our chemical formula. We know it's a 1. So there we have it, y'all. A quick summary. We have coefficients, the big numbers in front that tells us the number of molecules. We have state of matter in those letters in parentheses that tells us the state of each compound, whether they're solid, liquid, gas, or the important one, AQ, aqueous. And last but not least, the subscripts are those small numbers at the bottom that tells us the number of individuals of each element in a molecule. And now we get to the good stuff, the law of conservation of mass. When a chemical reaction occurs, new compounds are created. And here's the important part, y'all. But no new matter is created or destroyed. The atoms are just rearranged as the atoms change partners to form new compounds. So on page 10 for law of conservation of matter, I want you to write the statement here. No new matter is created or destroyed. And if you're really feeling it, you can just put atoms are just rearranged. In this visual here, I see that there's 1 carbon atom on the reactant side and 2 oxygen atoms, or 1 oxygen molecule. And on the product side, I see that I have carbon dioxide, which is made up of 1 carbon atom and 2 oxygen atoms. Now, the law of conservation of matter says I'm not creating any more carbon, so the carbon on the left-hand side will show up on the right-hand side. So again, I'm labeling it for y'all. I have 1 carbon atom on the reactant, and I have 1 carbon atom on the product side. Same thing with the oxygen now. I'm going to label it for y'all. So I have 2 oxygen on the reactant side, and on the product side I have 2 oxygen atoms on the product. So this is the law of conservation of matter. I'm not creating or destroying any atoms. All the atoms that show up on the left shows up on the right-hand side. The only difference is that now they've been rearranged, so my carbon is kind of nudged its way in between these 2 oxygen atoms. In addition, we can summarize this and say that the number of atoms in the reactants equals the number of each atom in the products. Okay, so this is a good summary that I want you guys to write down. And I want you guys to write down that the mass of reactants equals mass of products. And let's see this example play out. So I see that the mass of 1 carbon is 12 grams, and I got this number by looking at the periodic table. And also by looking at the periodic table, I see that the mass of 1 oxygen atom is 16 grams. And since there are 2 oxygen atoms, I have to take the mass of 16 and multiply it by 2, which gets me the mass of the oxygen molecule to be 32 grams. So those are the mass on the reactant side. Now I take a look at the product side, and I see I'm going to be adding that 16 grams of the oxygen to the 12 grams of the carbon to another 16 grams of oxygen, and the grand total would be 44 grams. And that's the product side, y'all, 44 grams. And now if I were to take the mass of the reactant and add them up, which I'm going to do, if I take 32 grams, add it up to 12, I get 44 grams. So the mass before equals the mass after the reaction. So again, the mass doesn't change. The mass of the reactants equals the mass of the products. So be sure, y'all, that you have written down everything that started on this slide. That the definition of the law of conservation of mass is that no new matter is created or destroyed. That the number of each atom in reactants equals the number of each atom in the products. And last but not least, y'all, which is a very, very important point, that the mass of the reactants equals the mass of the products. Now let's move on to page 11 in your spiral. The simplest form of a chemical equation is a word equation. For example, potassium metal plus oxygen gas yields potassium oxide. We will rarely use this format in class, but I wanted to show you a version of this. Here, my reactants appear on the left side of the arrow. This plus sign, y'all, represents reacts with, and then the arrow means yield or produces. And then again, if there is a plus sign on the right-hand side, that's the same thing as plus or in addition to, and products appear on the right side of the arrow. Let's take a look at these symbols here down on the right-hand side. We have the plus sign, and this is used to separate 2 or more reactants or products. The forward arrow separates reactants from products. So again, the reactants are on the left-hand side, and then the products are on the right-hand side. We will rarely see this here, or actually we won't see it at all in chem, this double-sided arrow, and it's used to indicate reactants and products and show that this reaction would be a reversible reaction, meaning it could go forward and backwards as well. Next, we have something called a skeleton equation. This shows which atoms are involved, but it doesn't tell us how many molecules are involved. So for example, this model here shows a methane molecule, which is 1 carbon and 4 hydrogen atoms. Again, it reacts with oxygen, which has 2 oxygen atoms, and it produces or yields carbon dioxide, a 1 carbon atom with 2 oxygen atoms attached, and a water molecule. So, like I said before, the skeleton equation just tells me who the reactants are and what products they're making. But what's missing is the number of molecules involved in order to keep the law of conservation of matter. So the law of conservation of matter states that if I have 4 hydrogen atoms on the reactant side, I should have 4 hydrogen atoms on the product side. But guess what, y'all? We don't. We only have 2 hydrogens. So we already know that this is not balanced and it doesn't keep up with the law of conservation of matter. So we need to do something about that, right? If I take a look here, the carbon seems to be conserved, meaning 1 carbon on the left, 1 carbon on the right. And for my oxygen, I have 2 on the left, but 3 on the right. So what can we do? There is a way to fix the solution. So let's check it out. In order to fix the issue from the previous slide, we're going to have to write a balanced chemical equation. So a balanced chemical equation shows all atoms and coefficients, and it tells us how many molecules and atoms there are. Okay, so balancing ensures that the number of each atom is the same on both sides of the reaction arrow. So it keeps the law of conservation of mass. Whatever is on the left side, the reactants, whatever we started with, will end up in the product side, but just rearranged, or we changed partners. So we take a look at our example from the previous slide, and we have a CH4 plus 2O2, so that 2, that's a coefficient that was added in order to make it balanced, creates carbon dioxide and 2 water molecules. So let's count it out, y'all. I'm going to draw it and count it out. So our methane, we have 1 carbon, so I'm going to write down C, we have 1. We have hydrogen, we have 1, 2, 3, 4. Oxygen, again, I'm going to count out each one. 1, 2, 3, 4. That's the reactant side. Now on the product side, I'm going to count 1 carbon. So this checks out. Both the left side and the right side are equal. Now hydrogen, I have 1, 2, 3, 4. So left side equals right side. And finally, I have oxygen. 1, 2, 3, 4. So both sides are even. So the left side of the arrow is equal to the right side of the arrow in terms of the number of atoms. And we can take this one step further. If I were to take the mass of methane and the mass of oxygen and add it up, it will equal the mass of carbon dioxide and the 2 water molecules. So again, just like the number of atoms are equal on both sides, the mass of the reactants will always equal the mass of the products in a balanced equation. Okay, y'all, that is it for today. Y'all have a good one.